Hey, what's up, guys? Welcome to another episode of the Modern Goonies podcast. I'm your host, Trevor King Minor, hanging out with my badass co-host, Michael Ross.
It's your motherfucking boy.
All right, I like it. All right, so welcome to Season 1, Episode 5, and today's topic is black holes. And I guess we're going to tack on gravitational lensing at the end of that. Is that what it...
I mean, we could talk about it at some point.
Okay,
it doesn't necessarily have to be at the end.
Okay, I gotcha. I know Michael wanted to include that, and I'm way out of my element here. Once again, all the super sciencey stuff, Michael knows way more than I do because he's got fucking master's degree in physics over there.
Not yet.
Not. We're gonna go ahead and we're gonna premature that one. Okay, so yeah, I've got some notes, so we can just like hop right into it. So the only real like research I did for this one was I was just kind of looking at a lot of the Kyrgyzstan videos. And then, like, I really like that PBS Space-Time guy. Like, he's like super bland Australian guy. He's just like, and when he goes into the black holes, and it's like just such a not radio voice to listen to this guy fucking talk. But he explains stuff like pretty well sometimes.
Sometimes.
So that's, do you know who I'm talking about?
No.
Oh, okay.
I was just remarking at your use of sometimes.
Sometimes. Well, yeah, because like sometimes he'll like be talking about shit, and it's just like, and he's doing it super blonde, and he just starts going into like this crazy, like he starts like simple and then goes into like crazy fucking detail. And I'm like, this is I just wanted to watch a video about like a black hole, and now I'm learning about like the way that light travels at 45-degree angles and weird fucking shit. I'm like, okay, it's like, this is too much. So what did you do to prepare? What are some things you'd like to talk about? Because I have some things listed out, but you go right ahead because this is your element.
Okay, so one of the coolest facts about black holes that I think is very interesting is that they can extract the most energy out of an object, like out of anything in the universe. Like,
really?
Nothing that we have comes close to the amount of energy that a black hole can take from something.
Oh, you mean like, okay, just it like taking it from something. So it doesn't have like the most energy, it just eats it.
Well, okay. I guess to effectively explain this, if we had, say, a pound of cell phones or some shit.
A pound of cell phones. All right, there we go.
First thing I saw.
1 pound of cell phones.
If we had a pound of cell phones and we used our pound of cell phones to power a nuclear fission reactor.
All right.
Then, assuming that this was as good as uranium-238, 0.05% of the mass of our pound of cell phones would actually be converted into usable energy.
Okay.
A black hole would be able to take 5.7% of all of the mass.
A pound of black hole.
No. No, like, it would be able to turn 5.7% of the mass of our pound of nuclear cell phones and turn that into energy.
This is a fucking dangerous lab that we have right now.
That is 114 times greater energy production that a black hole could do. I mean, quote unquote production. It's turning things into energy in the form of heat isn't really useful next to a black hole. I mean, at least not that I can think of, because it's a fucking black hole.
Yeah. Well, I was reading this one thing of like how you could basically, you know, because you know what a Dyson sphere is, right?
The thing that goes around a
sun.
typically stars.
Yeah, to harness its energy. It's a super theoretical thing, but you could do it. But apparently if you put one of those, but like just a bunch of giant mirrors around a black hole, and every now and then like you opened it up and shot like energy into it, it would like produce a shitload of energy. Like basically it'd be like this infinite source of energy if you could like harness it. It's like crazy nuts.
That's cool.
Yeah. So one thing that I didn't know about black holes is, so like, I guess the way that like fusion happens like within a star, because you know more about this because you know a lot about like neutron stars, right?
I know a good amount.
Okay, yeah. So like, and I don't know jack shit about them. So like, I'll kind of skip over that aspect of it. But I guess like when like, you know, there's a lot of like nuclear fission, fusion. I don't know the difference, whatever.
Fusion is when atoms combine. Fission is when atoms split.
Okay, so one of those, and then within
fusion.
Within a star, and then so elements apparently like it like turns into like iron in the center because it just gets like so dense and so hot. Like the thing that they like start like morphing into is like iron in the dead center of a star.
So the reason behind that is when you fuse nuclei, the most like iron is the first element that it takes more energy to fuse than you get out of it when it splits.
Okay.
So everything up to iron, you still gain energy when you fuse. But the star doesn't have enough energy to fuse anything past iron because it wouldn't get as much energy out of the fusion as it put in.
Yeah, you see, I didn't know that, and I thought that was crazy. I didn't realize that like at the center of a star after like a long time is fucking iron, basically. And then so the way I understand it is that the what is it like the usually stars are kind of in balance between like radiation and gravity.
Pressure and gravity.
Pressure and gravity. Okay, okay. And then at like a certain point, I guess like what is it? The pressure kind of outweighs the gravity, or is it the other way around? The gravity, I can't remember.
If gravity wins, the star collapses.
Okay, that's what I'm thinking of. So eventually, like its gravity within just gets like so fucking dense, it just implodes on itself, completely collapses, and then boom, you either have like I think that's where it can turn into a neutron star, and or a black hole.
Yeah.
Just kind of depending. So like, what's like the deciding factor of like it's going to become a neutron star or nah? This is a fucking trapdoor now.
The mass of the star.
The mass of the star.
Yeah. So fantastic. I'm glad you mentioned this because I actually. I wrote some stuff on this. So this is going to tie into the iron thing that you were just talking about. So not all stars are capable of fusing iron. Like that takes a lot of energy. And to do that, you need to have, or the star needs to have a high mass. And that's why, I mean, to my knowledge, there aren't a lot of white dwarfs with iron in them because a white dwarf is a remnant of a smaller mass star, which typically only has enough energy to fuse like up to, I want to say either carbon or oxygen. So once you get to about, I mean, these are very rough numbers, but if a star is roughly 35 or up to 35 times the mass of the sun, between 10.5 and 35 times the mass of the sun, then it will probably turn into a neutron star based on what we know about physics. There's a little bit of uncertainty there, but to turn into a black hole, the range estimate is between 50 and 150 solar masses for the black hole, or the progenitor star's mass, which is the star that creates the white dwarf, neutron star, or black hole.
Okay. So what's the difference between a neutron star and a white dwarf?
So a white dwarf is basically just the core of the star exposed. A neutron star is also the core of the star, but it's a lot more massive because the core, like at this point, there would be, like it would be an iron-ish core. It would have iron in it. And then it would eventually get hot enough to where that iron just disassociates into atoms, neutrons, protons, electrons.
Okay.
I don't believe white dwarfs get that hot.
All right, makes sense. So when a star does implode on itself and becomes a black hole, is that pretty much always going to generate in a supernova? Like for it when it collapses, is that what essentially a supernova is?
Yeah, a supernova is when the outer layers of a star, so the star collapses, and then the outer layers of the star are just ejected. Like when a star dies, it runs out of fuel. It's almost immediate. Like star runs out of fuel, a shockwave goes into the star and then immediately ripples back outwards, almost at the speed of light.
Shit, okay. So then, yeah, and like that's like, isn't that like the craziest like celestial thing that we can see? Like isn't basically just like a gigantic fucking explosion in space?
Yeah.
Yeah, okay. That's insane. I can't even like wrap my head around the amount of power that would have, because at the point when stars like collapse, they're like red giants, right? Or usually, and so they're way more massive than our fucking sun, and then they explode.
Yeah.
Goddamn. That's fucking nuts.
There are red giants, and red giants typically go into white dwarfs, or turn into white dwarfs. And then there are red supergiants, and then blue supergiants. And those are the hottest and largest stars. And that's where you get your black holes and neutron stars.
Okay. Yeah. I don't want to get too into the weeds on the stars because I know that's like a topic that we'll have later on the line in the seasons. So I guess we'll go ahead and hop over to more of the black hole side. So all right. So boom, star collapses. You got a black hole.
Yep.
And me just trying to like wrap my head around how fucking weird these things are. I can't even accurately describe it because, when you're watching this Kyrgyzstan videos, they say that space is kind of like a stage that is kind of like a waterbed. Like, the more mass something has, the more it like kind of dips down. And then you just see like the representation of a black hole. And they say it's like having a fucking trap door in a stage. And you just see like how much like space-time like sinks down because of how fucking dense this thing is.
Yeah.
I thought it was funny because they were trying to describe something, and they're like, all right, now say you're cleaning your room, and you just got like a bunch of pile of socks, like just in a pile. Like, and eventually at a certain point, like there's so many socks you can't get any more into your room. It's so compact. So then you throw one more in, and it's just so dense in the center, your fucking room collapses into a black hole. And it's these things are just fucking weird. So let's see. So one of the things that I didn't know about them. So some of them spin. Actually, like I would say, like almost all of them spin, don't they? Because usually when we're like doing a black hole in math, we think of it in terms of like the eternal black hole where it doesn't move. It's kind of been there and always been there, and like that's what works the best, like mathematically. But in actuality, they're spinning.
Yeah.
Because what is it? Because a singularity of just like a regular black hole would kind of just be like a point like somewhere in space, but since they are rotating, like you can't have an actual like a rotating point in space. So what the singularity actually is, and so you could probably we should maybe describe what a singularity is more than anything else. So you could probably describe that better than I could.
So you can think of the singularity as a point, but I think of it just as an infinitely small sphere so that it's three-dimensional.
Yeah.
But it's a very, very dense area in space where a shit ton of mass is concentrated.
Yeah. So basically, when we're seeing a black hole, what we're actually seeing is the event horizon. So we're seeing where the light can no longer, or the light is basically like being sucked in, it's being warped like around it, as in, the picture that we've that came out like 2 years ago now or something like that.
The Event Horizon Telescope.
Yeah,
picture.
and which was amazing because that was the first like confirmed picture of a black hole, right? Like
yeah.
We always knew they were there. We could see them in math, and like we could see like how things interacted in space, and we could tell it was there. But that was the first like photographic evidence of a black hole.
Yeah. So I would like to go back to the spinning black holes.
Oh, yeah, go ahead.
So that is caused just by conservation of angular momentum. So when things spin, they have angular momentum. And typically things in space spin because there's not really a lot in space that can prevent them from spinning. Like there isn't a whole lot of friction out there.
Right.
There's some, like photons can cause friction, but not enough to meaningfully stop angular momentum on a scale that we can see.
Yeah.
So if a star collapses, it's like a star typically spins.
Yeah.
And if a star collapses, then it's whatever it spawns is also going to spin. That's actually why neutron stars spin so fast.
Yeah.
And that's why black holes spin, because of angular momentum conservation.
Yeah, makes sense. And so going on what I was saying, like when we look at a black hole and we see that the way that light bends, like that's the event horizon. But what we're actually talking about is kind of like the all-encompassing, like aren't we really, when we're talking about a black hole, aren't we really actually talking about the singularity of it?
In my mind, when I think of black hole, I think of event horizon, accretion disk, do you know what, for the people who don't know what an accretion disk is, it's a ring of very hot material around a black hole. It's the things that you think of, like just look up picture of black hole, and you'll probably see like something that looks like orange fire around a black circle.
Yeah.
The orange fire-like stuff is the accretion disk.
Yeah.
So when I think of black hole, I think of accretion disk, dark event horizon, and then at the center of it, the infinite or near infinite mass.
Yeah.
Effectively infinite.
Yeah, and that would be the singularity, kind of like the point where everything is like so dense that like if you pass an event horizon, you're going to that fucking singularity, like you're heading straight for it.
Yeah.
And so one of the things that I had always viewed singularities as that, just kind of like you said, like an infinite point. But I didn't realize that, like I mentioned a minute ago, that most of the time when we're talking about a black hole, it's kind of like in its most perfect base form. Like we're not really talking about one like in actual, like in nature, and most of them are spinning. So what they think that singularity looks like is more like a ringularity. So it's kind of like an infinitely dense like circle, and it's fucking weird. That blew my mind. I was like, yeah, that was pretty crazy.
Yeah, I've heard of that, and that's actually something I don't quite understand.
Yeah.
Like when I heard it, I think I just accepted it and then forgot it.
Well, that's the thing about black holes is that once you kind of pass the event horizon, like our laws of physics are pretty fucky inside. Like, because Kyrgyzstan was basically saying that like once you cross that threshold, like actual time travel would theoretically be possible within that space before you hit the singularity. So that's why they're saying like it's probably a good thing that nothing can escape a black hole because everything is just probably so fucked inside that we don't really have any good idea. So this was something else that I had always kind of like knew. So this kind of ties more into the interstellar part. So like so the theory of like relativity, I'm assuming. So like you get near you get near a black hole, time is going to move differently.
Yeah.
Yeah. You
sorry.
just go in it. So if you get near a black hole, time moves differently. So what is it? It's normal for you, but for everyone else, like it's like so much fucking time has passed, like as you get closer to it. So I didn't know the actual term for that, and so like usually, so in reference to a spinning black hole, what it's basically doing. So like when we usually think of a black hole, we think of kind of like it's literally just like falling in a fucking hole, basically, like just essentially. But when we think of a spinning black hole, time around it is it's like a space drain. So it's like a whirlpool in space, basically.
Yeah.
And so that little area, as like the area that's like kind of spinning before you cross into the event horizon, is what's known as an ergosphere. And that is where, like, if you kind of like get sucked in and you were just like whirling around a little bit and then you pop back out, like so much time would have passed, it would have been fucking nuts. Like, so that's where like the kind of the concept of interstellar is kind of like within that like ergosphere. Like, hey, we're getting near it. We're like rotating, and like you shoot out of it, and who knows how much time has passed. And it's just absolutely crazy. So like that, if you wanted to do like time travel, you just get near a black hole and then pop out, and you're in the future. Like,
yeah. I guess an important thing to note about that is obviously you can't go into the past. Like when you think of time travel, you think of forwards and backwards. This is just
forwards.
Yeah. Any amount of mass causes time dilation.
Mm.
And I mean, that's what Interstellar does.
Yeah.
Like the main character, I think his name is Matt or whatever the fuck. Steve.
I don't remember what his name is. It's just Matthew McConaughey.
Yeah.
So.
Yeah. Whatever his character's name is, he says this little maneuver cost us like 84 years. That's talking about relativity and how the people that are on Earth are not close enough to the black hole to experience time dilation, but also moving very quickly causes time dilation. So moving at the speed of light causes so much time dilation that no time passes while you're moving.
Yeah.
And then the people say, we're on the third floor of this apartment complex.
Okay.
The people on the first floor experience slower time than we do.
That's crazy. I'm sure it's like a fraction of a second.
Yeah,
but
it's next to nothing. But
yeah,
we are dying faster, ever so slightly faster than the people 20 feet below us.
Damn.
And these relativistic effects are observed most near a black hole and when traveling very close to the speed of light, or a considerable amount, or a considerable fraction of the speed of light.
Yeah.
So like say 10%, 20% of the speed of light, you'll start to see stuff like that.
Yeah, that's just insane. Well, yeah, I can't even like wrap my head around how that even works. Like it just doesn't. None of that makes any sense to me. But one of the things that I thought was cool. So they were mentioning that if you were like, say, you were in a spaceship and you were just watching a guy fly into a black hole, and they would all of a sudden, like, to you, you're moving fucking quick. Like you're going like head ass into this black hole. Fucking you're going rapid speed into this thing. But like the people in the spaceship watching you are like watching you just basically like inch in slow motion. Like you're just going in slow motion and you're like, fuck. And then eventually you completely freeze in time compared to the guy that, so like the guy that's watching you, like he thinks that you are just completely frozen in time. You're just there for an extremely long time. You turn red and then it looks like you fade out of existence. But it takes a long time. So it's like, I don't even know how long that would be, like years, months, or whatever. That it just looks like, hey, Michael just froze. Like it's like a fucking glitch in the Matrix.
Yeah. And I guess you've already said this, but that's just because, I mean, at that point you've crossed the event horizon and no other information about where you're at could be seen by anybody.
Yeah, no, it's literally once you cross the threshold, there is the point of no return. They described it really well in imagine you're swimming in a river, and at the end of the river, there's a waterfall. So for the most part, you can swim in this river and be fine. But at a certain point, you're going to hit a point in the river where it's going so fast that you're going to go over that fucking edge. And that's kind of like what it's like as you get near a black hole. Is that like once you cross that, you're falling off. You're going to that singularity, and you're going to fucking die. So something else that's really cool about it is so when you approach it and you go in, the way that a black hole is kind of like sucking in and bending light, as you're going into it, you would literally see the back of your own head because light travels around, like I think so unbelievably quick around the black hole that you're literally seeing like a reflection of yourself as you're going in. So like how nuts would that be? Like you get near it and then you just see yourself like ahead of you as you're falling into this fucking thing.
That would be crazy.
Yeah, they said it's like the craziest funhouse mirror you'd ever experience. Yeah, that's insane. Oh, do you have something?
Well, that is, I mean, that's kind of a good segue into gravitational lensing, actually.
Oh, okay. All right. Yeah. So I don't know what the fuck this is. So what is gravitational lensing in just as layman terms as you can possibly describe to me?
Gravity bends light.
Oh, okay. All right.
Layman's terms.
Gravity bends light. All right. So then go ahead.
So light sorry, I guess I was facing downwards when I said that, but light travels through space. And if light encounters a massive object, then if the object has enough mass, the path that light takes will bend around that object. And the implications of that are you can see an object, like you can see light from something that is directly behind our sun, for example. Like you'd have to figure out how to filter out the sun and to see the thing around it. Mm-hmm. But that would to give you another example, just let's pretend our planet was incredibly massive. Mm-hmm. With gravitational lensing, we could see behind the planet if we were looking at one side of it. Like we could see part of the opposite side.
Really?
Yeah.
Okay. That kind of hurts my brain to just think about.
And that's just because of how the light travels through space-time. Like, space-time would be so curved that the path the light would take would be around and then towards us.
Jesus Christ.
Yeah.
The only thing that's coming into my mind is my fourth grade self. Like, hey, look, like if you hold your hand a certain far out, look, I can see through my fucking hands.
Yeah.
Yeah.
But imagine being able to see behind your hand. Like, you could see, like you could watch yourself pinch your skin.
That's fucking...
Just by looking at your palm.
Jesus Christ, that's fucking weird.
Gravitational lensing makes it look like an object is not where you think it is.
Okay.
So now this might be a doozy. I'm not really sure. But imagine, let's pretend that there is an object that is directly behind the sun.
Okay.
So the way the light bends around the sun, when we see the light from this object, it appears as though it's, say, I don't know, 600 feet to the right of the sun.
Okay. It looks like it's 600 feet to the right of the sun, but it's actually behind it.
Yes.
Okay.
So that creates like a false perception that has to be accounted for in math.
So it's like the space-time equivalent of objects in mirror are closer than they appear, or further than they appear, technically, yeah?
Yeah, you could think of it like that.
There we go. That's how I choose to think of it, because I'm a fucking moron. This reminds me, it's not the same thing, because this has to deal with like how fast light travels. But when you're saying this, it reminds me a lot of, so like, you know, if you're a certain million light years away, or say you're 50 light years away, and you look down at the Earth, and you had like a massive telescope, you can see everything that was going on, and you can see 50 light years away, you would see the 1970s. Like you'd see Nixon in office, you'd see like all this crazy shit. And so like to them, people who are 50 light years away, like it looks like, like look at these fucking primitive ass monkeys. Like they're in the 70s, like they don't know what anything is. They don't have the internet. They can't look at memes.
I mean, I guess we still don't know what anything is if we're saying the 70s is...
No, if you're born in the 70s, you're a fucking moron.
Yeah, fuck you.
Hi, Dad.
Hi, Mom.
Damn, yeah, no, and I always thought that was like crazy. So basically, and I know we might have talked about this a little bit on the, you know, as far as like the frontier of space, like the final border of space, but most of what we look at in the sky has been gone for a very long time. Like it's either past the point of no return where we can never see it again at a certain point, or those stars are dead, like they're not there anymore, or those planets have fucking blown up. Like they are completely gone. They're like millions, like we're seeing what they looked like millions of years ago.
Yeah.
And that blows my fucking mind.
I think it's crazy, but once you... I mean, that feeling never really goes away. You accept it.
Yeah. Well, yeah, it's one of those things that I just forget about like all the time. Like when I'm looking at the stars, I'm like, oh, stars are pretty. But then I'm like sitting there thinking about it, it's like, if there was any life out there, it is fucking gone and dead, and all those planets and stars are fucked. We're all fucked. We're all going to die.
Yeah. Same shit. Same shit.
Damn.
Now, there's another thing that I would like to mention.
All right.
And it's something specific to a black hole.
Okay.
So I'll just start with an overarching concept: orbits.
Okay.
So orbits are either circular or elliptical or oval shaped.
All right.
For those of you who don't know what an ellipse is, it's an oval. So some math says that you can have either a stable elliptical orbit or a stable oval shaped orbit, or you can have a stable circular orbit. And if you plot the potential energy, or the potential energy from orbit of certain objects, then on some of their graphs, there's a point where you can see the closest circular orbit that's stable to the object.
Okay.
So, that just means the closest that I can be and have a stable circular orbit.
All right.
So the only object in the universe that is inside its closest stable orbit closest circular stable orbit is a black hole.
Okay.
So this is where you get into things that are mathematically possible but not physically possible.
Okay.
Like stars have innermost stable circular orbits, which is what it's actually called, ISCO. But that is inside the star, but outside of the core.
Okay.
So nothing is going to orbit inside of a star. It would vaporize. It would melt.
Right.
It would become part of the star.
Yeah.
A black hole is completely inside of its innermost stable circular orbit because like all of its mass is concentrated at the very center of it.
Right. Yeah.
And I thought that was really cool. Like the black hole is the only object in the universe that has that property.
Well, yeah, that is weird. That reminds me a lot of, so have you looked into the information paradox at all? Basically, so the way that they were describing this was, all right, so you have a piece of paper, it has something written on it, and like just in regular everyday physics, you burn that piece of paper, and it's now ash. Now, all of the information of when it was the piece of paper is still within the ash. So theoretically, if you could figure out every single, like the way the molecules were arranged and everything that's going on, you could put that piece of paper back together. And anything that has information to it, you can see what it was before. Theoretically, you could go back.
Okay, but I have heard that.
But a black hole, when it sucks something into it, it makes everything the same. So it kind of like crushes, condenses particles or whatever. And so basically they say if you were to take every single singularity and just look at it, they would all be identical to one another, like technically speaking, because there's no difference. So a problem is that one of the fundamental laws of physics is that, like, what is it? Information can't be created or destroyed, or
energy.
Well, yeah, so energy, but there's also something that involves like information. It's basically that you cannot destroy something's information.
Okay.
But a black hole does, or the way that we view them, it seems like that's exactly what happens, is it completely destroys the information that was within a particle or any kind of mass that passes through it. Which is like pretty crazy because, like, you know, our math works really well in describing the universe, but when it comes to black holes, it seems like black holes just kind of like fuck things up a little bit. Or as far as our current understanding is, black holes seem to like fuck a lot of things.
Yeah.
And that's one of them. So they had some answers to the information paradox, and I'm too stupid to like completely understand what those are. But basically, I think it was going back to like the socks analogy. It's like, you know, you keep throwing socks in, it becomes like a black hole. But technically, like, you know, you could still keep throwing more in, but like the room now has to get bigger to accommodate for everything that goes in it. And I think they say they can tell things do kind of like fluctuate when things do pass into a black hole, even though technically it can't take anything more in because it's already as dense as it could possibly fucking be. It imploded on itself. So one of the weirdest ones that I saw that kind of like solves this is that when you pass through it, like all of the information that it takes in is encoded within the black hole, kind of like a computer. They said the equivalent would be like taking a 3D thing and then encoding it to our computer screen here. Now it's 2-dimensional, but it still has all of the 3D information, and or like a book. So you have all the information of a book, and you just take it and you put it into a Kindle, which has like much more space for all of the information within the book, but it's still technically a book.
Yeah.
So they say if we were to look at something, we were to look at like a black hole. Say Michael Ross passes into a black hole.
Okay.
And from my perspective, you look like you've been imprinted on like a 2D screen. All of your information is in there, but you look fucked on my side. But on your side, everything is still normal to you. You're still a 3D person. Everything looks normal. If you look outside the black hole, everything's fine. But all of your information is like encoded. So they considered it almost like a quote unquote holographic universe or holographic black holes or something like that, where it's kind of like it works like a fucking giant computer. It like breaks all the information down, but it's in there. You just can never access it again. That, or, you know, some people think that when you pass through a black hole, you might be in another universe on the other side, or since we have no fucking idea what happens inside and things get like super fucky. And then there was the concept, and you and I have talked a little bit about this, but white holes. Mm-hmm. So then there was that concept is that like maybe on the other end of a black hole is a white hole where it's constantly spewing things out. But the difference between a black hole and a white hole is that, you know, a black hole, nothing can get out of the event horizon. So the white hole, everything is constantly being like ejected through it, and you could never go, you know, through that point of where things are being ejected. And so they say that is kind of similar to like some of the ways that they've described it to what a Big Bang is, because that was another thing. It's like, oh, for a white hole to exist, it has to be like infinitely far back in time. It's like, okay, well, that's kind of what the concept of a black hole is, and everything did just super expand and come out, and you could never go back through the Big Bang.
Yeah.
So some people theorize that, okay, maybe if a white hole does exist, it's on the opposite side of a black hole, and it does. Each one has to create its own like little offshoot universe.
See, I think this is where the fun is.
Yes.
Or like the fun ideas are, because this is something that science can't touch.
No.
And that's where your mind can just run wild.
Basically, yeah. No, I always think like the super theoretical stuff is fun, because technically like a white hole was literally just that. Like it was just like a fun equation that does technically like solve it, but is nothing we could ever possibly fucking test. There could be a million other answers, but it was like a cool thing that it was like a nerd's way of having fun with math. And that's kind of like how they came up with the concept.
I don't want to shoehorn this in, but I just don't know how to, like, I can't segue into this. So the largest known black hole is called Ton 618.
Ton 618.
I mean, TON 618, but I'm going to call it Ton.
Ton, all right.
So it's 66 billion solar masses. And that is actually more massive than the previously known largest black hole, Sagittarius A, at 61 billion solar masses.
And what is a solar mass exactly?
It's exactly what it is, the mass of the sun. So it's like it's 66 billion suns.
Jesus
in one
fucking Christ. And how do we know this thing is there? Like, can we like just see a gigantic black space in space?
Well, we can. So there are some equations that let you know how much mass is in an area based on how the light interacts with that area. And then in addition to that, you have to account for how far away the thing is. Like, I mean, that's called redshift, if we've ever talked about that. I can't remember.
I feel like I've heard of that concept in general, but I don't think you and I have discussed it.
So the light received from this area that the black hole is in would be redshifted because it's very far away and it has to go through expanded space. And as light goes through expansion, or as space expands, the light inside that space loses energy. So it tends to, if it were visible light, it would go more towards the red end of the spectrum, which is why it's called redshifting.
Okay.
So after you take into account the redshift and like a few other things, you can figure out like how much mass that light is being affected by.
I still just can't wrap my head around how fucking big, what did you say, 66 billion solar masses?
Yes.
That is unfucking godly.
Well, let me tell you something else that's unfucking godly.
All right.
This black hole is more massive than all stars in the Milky Way combined.
Yeah. How does that even, I guess that would just kind of be the byproduct of like several supermassive black holes combining with one another at some point, like intersecting, like galaxies crashing into each other that had black holes at the center, and they just kind of all consume each other.
Potentially, but this is a very early black hole. So if I'm not mistaken, that doesn't really fit in with stellar evolution. Like, this is something that still needs to be studied. Like, it's there. We need to figure out why.
Okay, so we actually don't have a concrete answer of why the fuck that thing's so big.
Yeah.
So it's a rip in space-time.
It very well could be. Who knows?
Go through that, you just die.
It's so big that people are considering creating a new class of black hole just for this thing.
Good God,
like,
damn.
There are stellar mass black holes, which are black holes that have masses comparable to stars, say between like the mass of one sun versus the mass of 150 suns. Like, those are stellar mass black holes. Then there are supermassive black holes, which are found at the center of galaxies. They're the really big ones. But this thing, if accepted by the scientific community, the new category would be ultramassive black hole.
Fucking Christ. Sci-fi at its finest. But...
And even crazier, the event horizon, the point at which no light can return from this place, is 390 billion kilometers in diameter. That is 1,300 astronomical units, or 40 times the distance between the sun and Neptune.
Oh my God.
It is enormous. I mean, I cannot even describe how large this thing is.
That's just horrifying to think about. Just this gigantic black void in space that eats everything.
We're going to talk about, okay, I mean, it doesn't eat everything, but we're going to talk about the Aerodyna supervoid eventually.
Yeah. Well, yeah, so that's actually, so I said something right there. I said, eats everything, which is actually kind of like a bit of a misconception with people who understand black holes. So black holes don't just like, suck everything into it. Like, that's what a lot of people think. So actually what you could do is you could take a our sun and replace it with a black hole that's, let's say, roughly the same mass and whatnot, replace it with a black hole, and everything would still orbit it like normal. Like, it's not going to suck shit into it.
Yeah.
It just has a point of no return. Kind of like, you know, you can go around the Earth, but the second you kind of get within its gravity, you're getting sucked into the Earth. So it's like, yeah, everything would be normal other than the fact that, you know, that there would no longer be a sun and you'd all fucking freeze to death. But
yeah.
Other than that, everything's normal. So yeah, it's a bit of a misconception that it just goes around eating things. But yeah, essentially once you get in, and then like that's the fucking hilarious thing is the potential spaghettification.
Yep.
Oh my god. So yeah, so if you get sucked into a black hole, Michael Ross, what is it? Like your feet are like traveling faster than the top of your head. So like you're basically getting like stretched out through space time, and yeah, like
you get torn apart.
Yeah, you get completely. Well, you see, like that's what I think is like funny. Like I don't picture it like. Well, I do picture it like, you know, you getting like fucking strung out like a piece of taffy. But I just imagine what happens is you get close enough and your legs just get ripped the fuck up from your body.
Yeah, I mean, I guess. I mean, I can't just say that at your hips. Eventually, at some point, like I don't want to say selects, but gravity selects your hips to be the point where it's like, okay, this motherfucker, we're going to increase the gravity here. Like, you know, no. Like, it would be progressive, and it would likely start from your feet and then move up. But when you're falling into a large black hole versus falling into a small black hole.
Oh, okay.
So this is where, like, the memory is kind of hazy, but I think it's safer to fall into a large black hole.
It is.
Like, at the end of the day, you're going to fucking die.
Yeah.
But I think if you fall into a small black hole, you basically just get vaporized. I mean, okay,
yeah.
Assuming you survive the vaporization, you're going to be torn apart really quickly.
Yeah.
But
basically.
And that's just because the event horizon is small. So you're much closer to the fucking Singularity, yeah. And so because of that, the forces of gravity are much more pronounced on your body.
Yeah.
So like a square inch difference, say, I don't even know how to describe this, but you would die faster in a small black hole.
Yes. Yeah, you would.
In a big black hole, you have a large event horizon. For example, the one that I just mentioned, ton 618, 390 billion kilometers. That's a long time to be traveling in the darkness.
Yeah.
I mean, shit, it wouldn't be dark for you, but I feel like I'm just going around here.
Well, these things are confusing as shit. They literally break the laws of physics.
Anyway, if you want to see what's inside a black hole, go to a large black hole and jump in it. Supermassive.
Yeah, supermassive black hole. That's what I want. Yeah, because like that, then you could actually like kind of see things. That's where you would experience like the weird time shit and stuff like not making any sense. But if you fell into like a small black hole, you would pretty much just be dead instantly. I mean, yeah, you're gonna die because that's the other thing is that like once you kind of like cross the event horizon, no matter which direction, even if you try to move in the direction of where the event horizon is to like pop back out, no matter what direction you move, it only pulls you closer to the singularity.
Yes, all paths lead to one point or one location in the black hole.
It's like jumping off a cliff. Like you're going to the ground. Like you can try to fly, but you're hitting the fucking ground.
Imagine jumping up and then moving down.
Yeah, that would suck. Once again, yeah, thing that just makes no sense. So one of the things while I was doing this, that Kyrgyzstan had a video on like mini black holes, and they had this like little section that made me laugh pretty good. And so they're like, all right, so what if like a mini black hole was to pop up on Earth just like suddenly, and it was only about the size of a coin, like a nickel. And they were like, would you be dead? And they're like, well, yes, but it depends. And so basically, all right, so you have one, two different scenarios. You have one that's like the size and weight of a coin. So it only has like the mass of a coin and it's a black hole. And then you have one that's the size of a coin, but the mass of like a regular black hole. So say Michael and I are standing in a room and a coin-sized black hole that also has the weight of just a regular coin pops into existence. So basically, what happens is because, and this was something we didn't talk about, but black holes radiate away their energy in the form of what we call Hawking radiation. So after a significantly long amount of time, a black hole does fade out of existence, but it takes trillions of years for them to lose not even 1% of their mass, of their total mass. So like they'll be there for eons essentially. So nonetheless, so mini black hole, size and weight of a coin, pops into this room with you and me. And so basically what happens is that it fades out in less than a second. Like it pretty much immediately like dissipates, like because of the way the Hawking radiation is and it's so small, and it immediately like phases out. But it releases so much energy that it's like several times the power of the Hiroshima bomb. So so if one was just to pop into this room, it would be there for not even 1 second, and then we would all fucking die.
God.
I guess not everyone, but like, Dallas would be leveled. And so there's that. All right. So then in the other scenario, it's like, all right, so now a coin-sized black hole pops into existence, and it's the weight of a regular black hole. Everyone's dead. Like everyone fucking dies immediately. So basically what happens is that the Earth itself starts to orbit the coin-sized black hole that's like within the Earth. That's like, so imagine everything just starting to orbit this room. And so it devours the Earth as it does it. So it kind of just gets like smaller and smaller and like is fucking destroying it. And so Earth is nothing but a hot plasma, like accretion disk around this coin-sized black hole. And that's it. That's what happens.
Hell yeah.
Quite the fucking difference.
One is species ending, one is not.
Yeah, one is just levels a city. So, I mean, that one sucks because that would be like, for whatever reason, I don't know, your coin just collapses into a black hole.
The poor dialysis center next door, huh?
Yeah, fucking. Well, I feel like there'd be a lot more problems than just people not getting dialysis next door. Oh man, people are gonna find out where I live. We're gonna be assassinated. I live in California.
I live in Montana.
We're together in the same room.
We are together. I realized that would not work.
It works. Now you're visiting. Fucking yeah. So I thought that was hilarious. And honestly, I mean, yeah, that's most of my notes on black holes. So you have any more facts? I know you have several notes over there. So
I've said all the coolest things that I can think about.
Steal the show, Michael. Steal it.
Let's talk about Interstellar.
Oh shit, you're right. That's a good ending point. All right. So Michael and I are going to watch the Interstellar scene of Matthew McConaughey yeeting himself into a black hole. And then we will get right back to you, and we'll kind of talk about that, and we'll go from there. That was pretty nuts because, I mean, I know when they did that movie, they consulted with like astrophysicists a lot, and so they had pretty much not predicted, but they knew exactly what an actual black hole would look like. So that looks identical to that picture that basically popped up years later of what an actual black hole would look like. So it was just so cool to see that 7 years before it ever came into existence, because like our math is so good, and like that was really awesome to see, because it was a beautiful movie. Like that's beautiful.
So that the scene where you're looking at the black hole from the outside, and they're talking about how they need to escape by using all the thrusters and shit. Like when you take a look at the black hole, the part of the accretion disk that's on top of the black hole, that sort of looks like a halo. Yeah. If I'm not mistaken, I think it's possible that is actually behind the black hole.
Oh, okay.
Like I'm thinking the accretion disk is just a ring around the black hole, but space-time around it is so warped that you can see what's directly behind the black hole as above it.
And that would make sense. Okay, yeah, that's pretty cool. So one of the things that they did, so I'm going to assume this is probably like a spinning black hole, because one of the things that they're doing there, like the kind of the section of space-time that they're in, and the scene I'm talking about specifically is where they kind of like launch themselves away from the black hole to, gain speed. And like, I guess I'm assuming they go back to Earth. It's been a long time since I've seen the movie. That's essentially where they're trying to go. They're trying to get to where they're trying to go, and they use the black hole to launch off. And so essentially the portion of space-time that they're in right there would be the ergosphere, because they're kind of they're in the drain part. And so there actually is kind of like a theoretical science thing for it. And it's called like Penrose something involving Penrose. And it is the concept that you could use the ergosphere around a black hole to launch in and essentially get to different sections of the universe that you need to go, or use it. Yeah, basically, you use it as like a large thruster. So that's an actual concept, like a scientific theoretical concept, and I think they portrayed it pretty accurately and pretty good. Because when they were talking about that on like the PBS Space Time, I was kind of thinking of something similar, and then I had forgotten they actually did that in Interstellar. So that's really cool to see. It's like the movie is really good to watch. It just is kind of like to see all the stuff that like we will never be able to see with our own eyes. Like they not predicted, but they describe it pretty accurately in the movie.
That concept is just like, I don't want to reduce it because it's incredible, but that is an extreme version of, I think, what happened with Voyager. Like the Voyager satellite went around the sun to gain energy.
Oh, yeah.
And now it's like out of the solar system. The Penrose process?
Maybe. That might be it. I don't remember the exact thing, but yeah, it was like...
Energy can be extracted from a rotating black hole.
Oh, there we go. Okay, yeah. So yeah, the Penrose process. That's essentially like you're watching like a cinematic description of Penrose process. So yeah, I thought that was really cool because I had forgotten that they did that. But yeah, beautiful. I didn't realize that when he fell into the black hole that he was pretty much like immediately inserted into like a tesseract. I remember that scene differently. I thought he would. I thought it would show more of him like seeing his own fucking head like falling in and shit. But no, I forgot about that.
Yeah, I don't really understand how it goes from Matthew McConaughey enters the black hole, tesseract.
Yeah, me either. Doesn't really make a whole lot of sense to me. I'd have to like watch a bunch of videos, but yeah, I mean, there were some things. I mean, it was a fantastic movie.
I agree.
By almost every part of it, but there's a few things here and there that are like a little dumb and don't really make sense. They're like, okay, that's for the sake of narrative, but overall, yeah, if you want to see like cool sciencey shit, watch Interstellar.
Yeah. And there's actually something I'd like to say about the tesseract.
Okay.
And that is, if you could view time instead of just experiencing it, you would sort of see, I mean, I can't say it would be the layout of the tesseract, but you would see time like the tesseract. Like you would see the progression of isolated moments. Like if I were to wave my hand, it's like I would see every frame that my hand was in a different point in time if I could view time from the outside.
Oh, so do you guys actually study like the concept of tesseracts in physics at all? Because you seem to know more about that than I do, because I don't know shit about.
So that, no.
No, okay.
I mean, I don't want to say we study tesseracts, but the thing that I just mentioned, like that's something that we went into sort of great detail in general relativity.
Okay.
But the idea of viewing time piece by piece is present in all levels was the correct word. All levels of physics. Like even in introductory physics, like you're taught at this instant in time, say this beer bottle is floating, like it drops from a height, and then at the, say like 0.1 seconds later, it's X distance below where it initially was. Like you're taught to view time in pieces.
Okay.
And viewing time in pieces is exactly what you could do if we could see time displayed on an axis or something. Like if we could see time as a dimension.
All right. Well, so I mean, I think that pretty much sums up everything that I got. Do you have anything else that you want to add before we say goodbye?
Don't fall into a black hole.
Yeah, don't fall into a black hole. All right, guys, thank you so much for tuning in to another episode of the Modern Goonies podcast. I've been your host, Trevor King Minor. This is my awesome co-host, Michael Ross, and we will see you next week for Season 1, Episode 6, and I'll tell you what the topic is on that day. All right, good night, guys.
Happy birthday.